So, Today we are actually here to see how we can fine-tune open source large language models and convert a normal chat model into a reasoning model. So, so we have seen that in February, after the launch of the DeepSeek R1 model, the entire AI industry has been completely revolutionized. Earlier, we were restricted to the O1 model, which showed some reasoning capabilities based on the OpenAI's reinforcement learning with human feedback algorithm, which was producing outcomes which were favorable to users' requirements. But still, it was there were some cases where it was hallucinating, and even who wants to pay so much cost for APIs for O1 models now? Finally, when we have open source models here. So today in this presentation, we will see how we can convert a normal chat model into a reasoning model. So a reasoning model, or you can say a model which self-evaluates self before responding to a user's request. It validates itself before just giving the response to the user, and there's a chain of thought process. So let's begin this presentation. So earlier, we had several problems which many of us came across while using GPT-4, especially in applications which were very safety critical. So we used to see that the model used to make up a lot of facts, invent references, and would produce information which is a lot fabricated. And we had no visibility or the transparency on how the model is producing that particular response. We only used to just send a particular request as a prompt and used to get a response back from the model with just a line at the bottom that don't trust AI for all the responses, just validate this for your own information. So that is why now we require reasoning models, which can actually give us visibility on from where the model is actually getting this particular response, what it is actually thinking in order to give us that particular response instead of just giving us what we need. So there comes the explainability for these black box models because of their a large number of parameters and large number of layers. We don't have that kind of transparency to see exactly how the model is processing our requests. So that is why reasoning models came into the picture to uh, produce a chain of thought process to tell the users how it is actually responding to our request. So let's see. So like earlier, like I said, like we had GPT-4 and Claude 3.6, which generally gave us the response directly as per our request. But when reasoning comes into the picture, the model actually has to think and evaluate before generating a response for your request. So it mimics human thinking and better logic and planning. So let's talk a little bit about the DeepSeek R1 model, which just got introduced. So this open source model, it just came out and it has surpassed several benchmarks in comparison to the O1 and O1 mini model, and also surpassing its previous base DeepSeek V3 model on which it is trained. So we can see that for the MMLU, for the SWE bench, on SWE bench, it surpassed OpenAI's O1 model and O1 mini model by O1 model by a small margin and O1 mini model by a huge margin. And for the MMLU and GPQA, which tests the model ability for problem solving, reasoning, and general knowledge across STEM-based questions. So you can see over here as well, the model is at par with open model, and which is actually great because as an open source model, it is performing at par with open model, which is actually pretty costly when you actually go for buying an API. It costs around $15 per million tokens. So we can see how better it is performing. And also for Maths and AIME 2024 benchmark, which tests the model's ability on mathematical problems. So we can see over there also it is outperforming the previously O1 model and the DeepSeek base model, which is the V3 model. And on the code forces, it is not surpassing it by a very small margin. So these are few benchmarks which the DeepSeek model, DeepSeek R1 model has actually outperformed. So let's just see a few of the features. I think many of us have started using the DeepSeek R1 model as well. I myself have started using the model. So it's actually pretty great when it comes to thinking aloud. So whenever you actually send a request, it generates a step-by-step response and produces more accurate solutions to complex problems by breaking down the problem and generating a chain of thought process without actually directly giving a response to the user. And because it is fine-tuned with reinforcement learning, so it goes beyond the supervised training approach, where earlier it was just supervised fine-tuning. So so the DeepSeek R1 model, it has actually uh, how the training process was done was basically uh, the secret sauce behind this DeepSeek R1 model is the GRPO reinforcement learning algorithm, which is the group relative policy optimization algorithm. And this algorithm is the main driving force for this reasoning model. And having huge number of parameters, it has 671 billion parameters, where when you actually send this model a prompt, 37 billion parameters are activated to give you a response. And then the model gives you a response based on its reasoning capabilities. And its open source nature allows even local developers and many businesses to customize the model according to their own needs. And so, yeah, these were few of the features for the DeepSeek R1 model, where it was also supervised fine tuning was also implemented on the model so that it can uh, produce more readability, and also it does not do language mixing, which it was previously doing. So these were a few of the features. Now let's talk about what is reinforcement learning, which we are going to do in this presentation. When we talk about fine tuning using reinforcement learning algorithms. So reinforcement learning is nothing but an agent performs an action on a given environment, and for that action, a reward is generated. And based on the reward, the model keeps on updating its parameters. That's it. Just a simple definition. Now, the reinforcement learning algorithms, how they have evolved in last few months, have completely changed how these models are now producing the output. Like how the GRPO mechanism is working. It is completely different from how the previously proximal policy optimization was working, and how these algorithms evolve. So the direct reference optimization is nothing but the traditional RL reinforcement learning mechanism, which I just shared with you, that based on a model's action, a reward will be generated, and based on the reward, the model's parameters will be updated. So let me give you an example to make it very simple to understand. So if a model has to grade two types of an answer sheets which belong to different subjects, let's say physics and chemistry, and if the model typically grades a high score for physics, let's suppose it scores 80 always, and for chemistry, it scores 40. So for 80, we are actually comparing with the total score of 100. So 80 being a high score, the model will reward a very high value, and 40 being a low score, it will reward a lower reward for 50 compared to 100. So because of this, what happens is the score which is high, which is at 80. So the reward will keep getting high for that particular answer, and not for the answer for which the model is scoring 50, because the scoring is relative to the total 100 score and not according to what the model is typically scoring. That is why we needed proximal policy optimization, where the model is not scoring based on the absolute score which it is generating. Because if a model is typically generating 80 on a particular subject, it is normal for the model to generate 80 or above again for that particular subject. But it is not But for the model who is generating a score of 40, and if it is improving by 20 marks, let's say 60, so it is not rewarded that much because it is still being compared with 100. And with 100, 60 is still less than 80. So the reward is less. That is why PPO came into the picture. So what PPO does is it assigns a line which is the baseline. So the model will be evaluated from 80. If it is generating 80 always, so it will be evaluated from 80. And if the model is generating 40, so it will be evaluated from 40. So, so next time when the model generates a score of 60 rather than 40, so based on that, it will be given a high score, which will lead to encouragement and model will be able to perform better. So the rich is not getting richer, while the poor is also performing more better next time. So that is what was the purpose of this particular optimization technique. And it also uh, uh, introduces a reference line so that let's suppose if the baseline is 80 and the model is suddenly scoring 99 out of 100. So it does not actually generate a very high reward such that such that it puts pressure on the model that it always has to generate a 99 out of 100, which will actually cause the model to hallucinate and even score below 80 because of that high score. Because of all these reference lines and the baseline, the computational cost gets high because the baseline also needs to be keep changing. So if a model is typically scoring 80 and it improved suddenly to 85, let's suppose, so the baseline has to be changed to 85. Now model has to be evaluated from 85, not 80. That is why the computational cost got increased. So now the GRPO mechanism came, which was introduced by DeepSeek. So what it does is it says instead of generating one response for a particular subject, let's say, you generate multiple responses, and for each response, you generate a reward. And then you take the average of the reward. Now, if the model performs better than that average, you get a reward. If the model performs lower than the average, you don't get a very high reward. So that is what the GRPO mechanism is, which we have shown here, that you generate multiple response, score each, and take the average as the baseline. So this is more memory efficient as you don't need to again and again dynamically change the baseline, the reference line, which we were changing over here in the PPO. When we had to change from 80 to 85, if the model is again and again scoring 85, then baseline had to be set to 85. So the computational cost is increasing. But GRPO this gets rid of this baseline mechanism which is used in PPO. So now let's see how we can actually fine tune these large language models and adapt them to our domain specific data set. So we know that initially how these base large language models are trained, that first you build an architecture for a large language model, and then on a gigantic data set, these are pre-trained. And for fine tuning, so earlier in the very conventional case, what it was done was we were fine tuning all the parameters of the model. So if we want to fine tune the DeepSeek model according to, let's say, another domain, like for example, banking, we want only the model to answer questions related to banking. We had to update all the parameters of the model, which is 671 billion parameters. And that is a lot and not at all computationally suitable. So low rank adaptation was introduced by Microsoft, which allows parameter efficient fine tuning. Now, unlike having to update all of the parameters, what low rank adaptation does is it freezes all of the original weights. So you can consider these large weights as a huge matrix consisting of rows and columns. And each column is either dependent on other columns or it may be independent as well. So how the low rank adaptation works is it drops all the linearly dependent columns because then you will compress the size of the matrix and again you will refactor it to the original uh, dimension, which is the total parameters. The linearly dependent will still be intact. There won't be any effect on that. So that is how it reduces the size of the matrix by a rank of R. So how it does is, so initially for any given layer, we have d by d billion parameters. for a transformer layer. And what it does is it compresses it by a factor of R. This is the hyperparameter for reducing the matrix to a rank of R. And after that, using the B matrix, we refactor it to the original dimension of D by D, and then add it to the pre-trained weights and get the total updated weights, which are sent back to the model. So that is how LoRa does this, so that we don't have to update all of the parameters. We will just update 1% of the total parameters. That's it. We are not going to update all of the parameters. And so yeah, that is how it works. So you can see it over here as well, that we will be freezing the model weights, and then only for the reduced parameters, we are going to pass it through the backpropagation algorithm, where the gradient is being computed only for the lower rank or the 2 into R into D parameters, when earlier we had D into D parameters. So for only these number of parameters, which is 1% of total parameters, the gradient is being updated, and the backpropagation algorithm is working for only these particular set of matrices. So now let's dive into fine-tuning the Quen 3 billion parameter model by Alibaba, and with the GRPO, and see how we can convert this open source chat model into a reasoning model. So I'll just share you the collab link in the chat so that you also can execute these code commands and everything alongside. So let's begin with the code implementation for this model. First, we have to set the environment where we have to install the Unslot library and VLLM. So we are using Unslot because Unslot provides an efficient way of including all of these different. It provides support for quantization and low rank adaptation, which we have to use for fine tuning our model. And also, it reduces the memory usage, which I will be showing you that it uses only 6 GB of our VRAM halfway through this code. So that's like pretty amazing. And it uses meta X-formers. And so we are using and also we are applying fast GRPO by Onslaught in order to use this reinforcement learning algorithm. So you have to first install these libraries and just restart your session. And before you start executing the code, please remember to change the runtime to GPU because it won't be supported by Onslaught otherwise. So once you install these libraries, then you can just restart the session and directly jump to this particular line of code, which will just jumpstart your Onslaught and initialize the GRPO algorithm. So next we have to load the model and the tokenizer. And I'll be explaining you these set of parameters as well, which we are passing as a part of the fast language model. So over here, we are using the we are assigning the max sequence length, which is the context window. We can increase it also for longer chain of thought process. Then we have set load and 4-bit to 2 so that it can reduce the number of, it can load it in 4-bit format so that it does not have that impact on precision while it loads much faster. You have to first change your runtime to GPU if you haven't done that. So without that, Unstart won't work. You have to install these libraries, and I'll explain you other things as well as we go. All of these, the working for these libraries as well.
So Ashutosh is asking where to select GPU. Can you also point that out?
Okay, so you have to go to runtime. In the menu, you can see over here, and you have to click on change runtime and click on T4 GPU. So you can then change your runtime, and it will show over here as well. Connect to T4 and over here, so you can see if the GPU is initialized. So yeah, so all these parameters you have to. So these are a few of the parameters as a part of the model where we are also setting the max LoRa rank, which is 64, which we have set over here, like LoRa rank, we have told that we will be setting it to 64. And also GPU memory utilization, we will be using only 50% of the GPU memory. And we can reduce it if we go out of memory. And then over here, we have to, using the parameter efficient fine tuning model, we'll pass the model parameter, then the LoRa rank, which we can choose out of these particular suggested ones. And then these are the target layers for which we want to fine tune our model. And you can remove the query key value and the output layers, which are these particular layers, if you run out of memory. And then this is the LoRa alpha parameter, which scales the rank, which scales the compressed matrix. And then we have use gradient checkpointing, which creates a checkpoint on each step. And uh, the random state parameter, which is like the seed parameter. And yeah, so after executing this particular code, you can so let's talk about the data set on which we are going to fine tune our open source model. So it is the GSM 8K dataset comprising of 8,500 elementary school math problems requiring 2 to 8 arithmetic operations to solve. And these are actually in many different languages so that we can make our model more robust. And we are using Hugging Face to load it. And this model has 7,473 training problems with 1,319 test problems. And each entry of each data entry includes a question answer pair. So, so yeah, let's dive into how we can how to have a reasoning model. So, how to actually convert a chat model into a reasoning model? So we define a system prompt. So for chain of thought process, we do some prompt engineering, which we pass as a as we do the prompting. So we define two tags, which are the reasoning tags and the answer tags. So the model has to give its chain of thought process within the reasoning tags, and the output it is going to generate within the answer tags. And the purpose of these XML tags is to segregate the answer and the reasoning so that when the model generates its response, we can see the reasoning as well as we can get the answer and we can validate it in real time. Now we have few set of functions in order to implement this. So we have the extract XML answer, which is going to extract the answer within these tags produced by the model. Then extract hash answer, which is the actual answer for that particular question stored in our database. And it is marked with with a 4 hash prefix. Then we have get GSM 8K questions function, which loads the training data set, uh, defines the schema for the prompt, and also extracts the original answers for all those questions. We'll be seeing all of this now. So don't worry. So here's the code for it. So first we are assigning the system prompt where we are telling the model to respond in the following format, where we will have reasoning tags and the answer tags. And we are defining the XML code format as well. And then we are having the first function, as I told you, where we are going to extract the answer produced by the model within the answer tags. Then we are extracting the hash answer, which is the actual answer for that particular question from the data set. And this is the GSM8K questions function, which first loads the uh, data, training data, and then maps the data in a way such that the prompt in the prompt, we are giving the system prompt for the model to generate the response in format of reasoning and answer, and the questions along with the actual answers to those questions. And on this, the data is going to be trained. Now we are yeah. So we have initialized the data set over here, and now we are going to define our reward functions, which will be used by our GRPO reinforcement learning algorithm. So first is the correctness reward function. So what it does is it extracts all of the response for the questions, which is in form of reasoning and answer. And then we have the questions, all of the questions for which the response was generated. Then we have extracted responses where we are extracting the answer for each response. And then we are saying that if the actual answer to that question is equivalent to the answer produced by the model, so we will assign a reward of 2. Otherwise, we will assign a reward of 0. Then we have the int reward function, which is similar to the correctness reward function. But over here, what we are doing is we are getting the responses. And after we are extracting the answers from the answer tags, we are saying that if the output generated by the model is in form of an integer, so we will assign a zero point 0.5 reward. Otherwise, we will assign a 0 reward. So if the model's output is in form of float, so then only this will, so if it's a digit, so it be going to reward the model. Then we have the strict format reward function. So over here, we have defined a regex pattern that the model should have, the output produced by the model should be in this particular schema such that you should have the reasoning tags and then the answer tags. So if we have this schema of reasoning and answer tags, and if that regex pattern matches in the responses generated for those questions, we will assign 0 0.5 reward. Otherwise, we will assign a 0 reward. And then we have soft format reward function, with which checks if the chronological order is correct. First, reasoning should be there, and then answer tags should be there. If that particular pattern matches, then it will assign a 0 0.5. Otherwise, it will assign a 0. So, and after that, we have count XML function. So, count XML is used for checking if the tag is correctly defined in the system prompt. So, so like over here, the reasoning tag is an opening tag and it should not have any slash. So, if it is correctly found in the text, so we will actually reward it with 0.125. And same way for closing reasoning tag, which has a slash. So if this is also correctly defined, we will assign a reward of 0.125. Then we have for the answer tags, we are assigning a penalty. And this penalty is being assigned because we don't want the model to generate anything out of those tags. We don't want any characters or any words to be uh, produced outside those answer tags when the model is generating its response. So we are assigning this penalty if the model will generate anything outside these tags. And we are using this function within the XML count reward function over here. And so by this particular way, we will be assigning the rewards. So all these things are mentioned over here as well. So if you want any more clarification, you can read these instructions as well. Now from the transformer reinforcement learning library, we will be importing the GRPO configuration file and the GRPO trainer. So with these two, first we are going to first we are going to define the GRPO configuration file, which will be used as the training argument. So we are first going to give these parameters over here. So first we will be giving use VLLM equal to true. So why we are using VLLM? Now we are coming to that over here. But because we are using GRPO, so GRPO generates multiple responses. And for each response, reward is being computed. Now we don't want the model to go and compute the reward in a sequential manner, such that, okay, for the first response, it will compute a reward. Then for the second response, it is going to compute a reward. We don't want that. It will be such a lengthy process. So what VLLM does is it calculates reward for all the, let's suppose if 8 responses have to be generated for one prompt, it computes rewards for all the 8 responses parallelly, such that you save on time and also on memory as well, and you make it more faster. So using VLLM, so we set that to true. And then we set a lower learning rate because we don't want too much variance and fluctuation uh, because of our reinforcement learning algorithm. If it assigns a very high or a low reward, then we are setting the coefficients for our random optimizer over here. And then we have the warm up ratio. warm-up ratio defines the gradual increase in the learning rate, because Adam is adaptive learning rate optimizer, and it keeps on adapting the learning rate. So we don't want it to increase the learning rate all of a sudden. We want the learning rate to be increased gradually. So after 10%, so it will be increased by 10% in the initial training process. And we define this parameter called learning rate scheduler type as cosine, which is used for decreasing that the learning rate if it is increasing too much. And again, directly then setting the Adam 8-bit optimizer over here as well. Then we have logging steps that after each step, logging will be safe for the model. And also, depending upon the kind of hardware we are using. So currently we are using P4. If we were using any other kind of a hardware like A100 or V100, so based on that, the precision for loading or the kind of data type in which we want to load the models, that can be changed. Load the gradients particularly. So, and then next we have per device training batch size, that because here we have only one device, which is which is one GPU. So we have per device training batch size to one. So only one response is being trained. So like in one epoch, we are training one response, uh, and then we have gradient accumulation steps to one, and number of generations is 8, so that for each prompt, 8 responses will be generated. And max prompt length is 256, that whatever response it will generate will be of 256. Whatever prompt which we will get or give, it will be of 256 length, and max completion length will be of 200. And then epochs is set to 250, and after 250, the model will be saved. And max gradient normalization is for flipping the gradient so that their value is not too high. And report to none, uh, it disables weights and biases. And output directory equal to outputs, it's a directory called outputs where we can save the logging and checkpoints. So yeah, and so now we can actually, so after initializing all of these training arguments, and also you can decrease the number of parameters, number of epochs, or increase it in order to get more uh, efficiency and performance on the model. So we have set it to 250 right now. So you can increase and decrease it according to your requirement. And so over here as well, we have mentioned a clear definition for each of the parameters. So if you want to, if you need any more clarification, so you can read these instructions as well for that. So over here, we have initialized the trainer, which is the GRPO trainer, and we are passing the model. Then the tokenizer as well, and the reward functions which we initialized. Along with that, the training arguments and the data set. And then we call the chain function, a chain method in order to train our questions and answer pairs. So over here, I'll just show you one table which is generated. I think it is the very first epoch. That is why it is, yeah, no, it has generated. Yeah. So you can see the reward values over here, along with other things like completion length and KL value. So KL penalty is nothing but the penalty which we talked about, that the reference line in the PPO, but you don't want the model to generate the rewards which are too far from the baseline, such that it puts pressure on the model to uh, always try to perform so much better than like so much better than every response. So KL penalty is that a reference line. So that is what KL is over here. And other parameters. So yeah, these are just rewards for each particular function. So yeah, so this will be trained for like 250 epochs, where you can see it is training for every question answer pair. And then after it's trained, so it takes some time depending upon the number of epochs which we give as the parameter. And after that, you can, so there is something called applying the chat template. So what applying chat template does is that right now we are currently training the model where we initially uh, gave our own system prompt when we wanted the model to generate its response in form of reasoning and answer tags. But it is not. But it is not everywhere. Like when we will be testing the model, we are not providing that system prompt. So we need to provide that system prompt in order to allow the model to in order to see that chain of thought process of reasoning and answer. So what we are going to do is before actually doing that, we are going to save the our LoRA model which has fine-tuned the lower set of parameters. And after that, we are going to apply a chat template, which will be in form of our system prompt and the question we want to answer. We want the model to answer, and we will set the parameter at generation prompt to true, so that the model can follow this particular. So that model has to generate the response in this particular format. So after this, we will be passing few of the parameters over here, like temperature, which controls the randomness of how the model chooses the tokens in order to respond, and also the top p value, so that the model always selects very high probability tokens in order to generate its response. And the maximum tokens it can generate is 1024. We can increase this as well in order to see more chain of thought process. And so over here, we are loading the LoRa model. We are passing the text, which is in form of our question, and the system prompt, which we want the model to generate in form of reasoning and answer tags, and then the sampling parameters. And over here, after like we have generated this response, so I'll just show you quickly how this response looks like. So over here, as you can see, we asked the question that how many R's are there, how many times the letter R appears in the word strawberry. So you can see the reasoning tags are now initialized to find how many times the letter R appears in the word strawberry. We can go through the character by character sequence in strawberry, and then we can see the letter R. It appears 3 times. So that is how it has generated its reasoning process, and also in the answer, it has generated that it is for the 3 times over here. So we can see how this model actually did that. It generated the response. And without actually giving the system prompt over here, we just applied a normal chat template. So the model gave a response in this particular manner without a reasoning and answer tags. So we don't want that. So that is why we actually gave our system prompt as well, and we applied that chat template. So this was the implementation for the Quen 2.5 GRPO model, Quen 2.5 model, which we fine-tuned using the GRPO reinforcement learning algorithm. So if you have any doubts and any questions, so we can now answer. Okay, yeah. Shubham, yes. Yeah.
Hey, hi. Hi, Utkarsh.
Right.
Uh, So I wanted to understand, we saw multiple reward functions, right?
Mhm.
Multiple
Yeah.
types of output that we were rewarding there, right? So why not
Yeah.
just reward the strict output and reward the partial outputs as well? Like, why do we reward just for getting the chronology right instead of
Okay.
sticking rewarding the strict format?
Mhm. So you're asking me, why do we need these fixed formats, and why don't we just have why do we need these extra reward functions? Why can't we just go with these?
Yeah, yeah. Like just the strict one. Let's
Hmm.
say the strict
Hmm.
regex, very strict regex, that checks for
Okay.
numerical output as well and strict format as well.
Hmm.
So that's
Okay.
my question.
So yeah, so the strict format is necessary because So firstly, I'll show you the uh, order of this. So yeah, so the strict format is necessary because to ensure that the model, whenever the model responds, its response has to be in a format where you have reasoning and answer tags. So whenever the model will generate a response, the chain of thought process has to be within the reasoning tags, and the answer has to be within the answer tags. So if this schema is not defined anytime if the model hallucinates, so it will assign a zero penalty. So the model will know that anytime if it is not generating this kind of if it is not having this regex pattern, so a penalty will be given to it. And for soft format reward function, it is that it will not confuse between, okay, first generating the answer and then giving the reasoning for it. It should show its chain of thought process first, and then it should be able to, based on that, it should give the answer, because that is how anyone can first actually see how the model is verifying how it is thinking on its own in order to give us a response. After it has generated a response, then it seems quite like like invalid that it is giving a response after
Yeah.
reasoning after
And
that.
yeah, Utkarsh,
Yeah.
I just want to add something to this. So basically, we have like
Yeah.
multiple verifier functions and also reward functions because there's also a use case of reward hacking. So even if you just reward if the answer is right, sometimes it can even generate something which is random. Instead of English, it might even have some math and even mix it with different language and come with a right answer also. Because that is how it does a reward hacking. So we usually have all of these rewarded. The format has to be right, the thinking process should be right, the answer should also be right. Sometimes it can even memorize the answer would be right. If you only define the answer to be right as the only reward, then it can just go and hack that reward and give you the right answer by memorizing it, but would not even actually think through that problem.
Okay. Okay. Yeah, makes sense. Thank you.
Anyone has any questions, you all can just raise your hand and I can unmute you one by one, and Utkarsh and Raj can go ahead and answer your questions.
Hi Utkarsh, Nidhi this side. You are on mute, Utkarsh. I can't hear you.
Oh, okay. Yeah.
Okay.
Yeah. Hi.
My query is that long back I have created one chatbot using long chain where I used open API keys. So the model which you showed right now. So have you used any key, or we can run it without any key?
You don't need any API key for this. This is an open source model. This is a Qwen 2.5 model. You can use other models as well, not only just Qwen 2.5. There is 5.4 model. Then you can use this model itself. It is the Qwen 2.5 model. And yeah, you can even fine tune Llama models as well.
Okay. So, can you just let me know how it can be done? Just if any
Yeah, sure.
is there or something is there, because I'm struggling with that.
So it's like over here, right? We are actually using the fast language model library, and from there we are uh, loading this pre-trained Qwen 2.5 3 billion instruct model. So
Okay.
that is how we can actually you can load it using Hugging Face as well. Over here we have used fast language model because
Okay.
we are using unslots to facilitate this process. Yeah,
Mm-hmm. Okay. Okay. Thanks a lot.
yeah,
Utkarsh.
yeah. Hi.
Yeah, I have a doubt how GRPO is better than PPO in
Yeah.
terms of the response, because the reference
Your
range
voice is a
is
bit inaudible. How is GRPO better? I lost you after that.
are you able?
Mukesh, you're very feeble. We are not able to hear you like very well.
Yeah, 1 second. Now is it okay?
It's
Yeah.
better, yes.
Yeah.
So, Utkarsh, I'm asking that how GRPO is better than PPO in terms of the
Right.
responses. Like
Okay.
in PPO, the reference time keeps on changing. but in GRPO, we are making the reference time constant. So by making that, we lose the accuracy or the betterness of the response.
So actually, what the thing is, PPO is also good. It's not like PPO is just overpowering GRPO. Many models are using PPO as well, but the thing is, PPO is really very, very computationally expensive, which is what makes it difficult for people like for example, if someone wants to do some simple testing, and if they want to fine tune a model, it becomes very difficult for them. And PPO, like I said, it dynamically keeps on changing the baseline. So if the reward is if the baseline is set to 80, and next time the model is again and again being stuck on 85, the baseline again has to be changed to 85. So because of that process, it becomes very computationally heavy. But with GRPO, it is just that it is cutting down on all of these things that dynamically you have to change the baseline. It just says that just take the average of all of these things. And based on that, you have to, if the model performs better than the average, so you are generating reward. Otherwise, you are not giving it a very high reward.
And one more, yeah, I'm sorry, I just want to add some more to this. I mean, one more requires a separate critic model to be trained.
Yeah.
So you probably
Yeah.
need to train a separate model. I mean, that is how the computation costs go high. The and GRPO, you are basically making use of the same model that is generating, right? What we are doing now with GRPO is we're using the same model to inference, and we're just telling, okay, just choose the best of it, and just iterate upon that. So then you're basically not have to train a separate reward model. And this here, but only one more thing is, uh, there's one limitation though, right? GRPO could only be applied for self-verifiable problems, right? Now coding and math, these both are self-verifiable problems. You know what is the end answer. If there is a problem, you don't want a separate model to say it is right or wrong, but rather if you're getting an output which is right, I mean, if it's a math problem, you know what is the answer, right? It is able to solve the problem to get the right answer. And coding as well, if given a problem, you can even test that through an environment where if the code is written properly, if there's a linting, or if that is not a proper syntax, you would probably get that directly. So it's more of a scalable solution is what GRPO is, whereas PPO is not that scalable. In terms of you probably need to have more computation. You should also have a separate critic model that needs to be trained, and there could also be quite complications in that when you have a separate model involved. So that's the reason why that's the beauty of DeepSeek. Like DeepSeek is able to limit that at the computation cost and able to get this RL, scale this RL end to end to develop some thinking model.
Thank you, Raj. Thank you, Karsh.
Hello.
Right.
Yeah, first, thank you for the session. Actually, I'm very new to the AI agents. Just been exploring. So, just last week, I was able to create an AI agent using N8N, a Telegram bot
Okay.
using N8N. Now, this
Yeah.
Quen 2.5 is very new to me, and even GRPO. All of these concepts are very new to me. So, I'm just trying to wrap my head around whatever I created in N8N. Like I trained my Telegram bot to do certain functions within the Telegram as a chat. So does that become a model that can be trained into this Quen 2.5, and how does that work? I'm just trying to understand that.
Okay. I think Tats will be able to tell you more about the N8N
Yes.
model.
Yes. So is it, Adi, so whatever you're asking, is it about like training? So you basically have a Telegram bot that you created, and you're asking whether you could able to fine tune or train that model using that agent, right? Or maybe using the data that is generated. What exactly? Can you please repeat that once again?
Yes,
I
yes. So
have, yeah.
for example, I just created a basic AI agent, which
Yes.
would mean that please read my message and let me know what to reply to
Yes.
this, for example.
Yes. Yes.
But what if somebody asks me a message of a code? They are
Yes.
asking me
Okay. Got it.
a reply to a code, but the
Yes.
Telegram won't be able to reply to that. Can Quen
Yes.
2.5 train that model to reply to that specific query?
Oh, okay. To that specific query, yes, you can. Do you think replying to a code is a good thing or a bad thing in this? Because usually, if there's a chatbot which is supposed to only answer questions to you regarding your company or anything, and if someone coming in asking it a code or maybe a Python code, do you think? That is what I'm thinking. Are you referring to Python code or something? Like it is asking if someone asks for a code, maybe it is not replying because it's not supposed to reply, right? Because if it is replying, then people can just get into your chatbot and use it like ChatGPT or something, right?
Yeah, this was just a basic example. This is on
Yes.
Telegram. It could be on other
Yes.
messaging apps also.
Yes.
Like
So,
just giving
so
a use case.
yeah. Yeah, so there are two things here, right? For LLMs, we are basically narrowing it down, its domain expertise to your own use case, right? If it is a chatbot that is working for you, your use case, so it shouldn't be, you add guardrails for it not to respond back by giving code. But if you really want to do that, most of the LLMs can do that. Most of the LLMs can already generate code. Maybe the quality might not be as much as best like GPTs because GPT has a bigger parameter model. But yeah, even Quen could do that. Even Quen could write some simple Python codes, and it is possible. You don't need any fine tuning there. You can just ask it, and it will generate you the code.
Okay.
But
Yeah,
And
but
even
usually
this is
the problem
possible.
here is how you can fine tune it, right? How you can put guardrails is what people usually say. How you can put guardrails and how you can avoid that. If some because there were a lot of issues where someone would come in and just ask any general question as well. Yeah.
got it. I have one more question if you guys have time.
Very sure.
Um, so there is a concept of human design. Just like we have personality trait concepts like you must be an INTJ. There are specific personality types, right? Similar to that, there are human design types. You could be a manifesting generator, a manifester generator. And basically that tells you what kind of personality you have. So let's say that me as a person, I have my whole human design concept with me that, okay, I am this type of human design person, and these are the traits which are the strongest in me. Like these are my strengths, these are my weaknesses, etc., etc., etc. And if I give all of this data, like this is my blueprint, if I give all of this data as a model to train on for to Quen 2.5 and then ask questions from it to predict in the future. Let's say I'm asking it, okay, 5 years down the line, I want to be this person, and if I am this human design person, show me the journey. How can I achieve that? Is something like that possible with this model?
So this model is for what we have done over here is we have done fine tuning with reinforcement learning. So when it will generate a response, it will give you the chain of thought response as well. But when you're talking about this particular thing, it is referring to the memory along with the knowledge base you will be providing the model. So,
And plus
so you can,
prediction, memory
yeah.
plus
So,
prediction.
yeah. So you have to either like separately have a memory as well, where you can like memory parameter where you can keep storing the context of your right, so that whenever you chat in future, the model has that context. But otherwise, if you are fine tuning directly on your knowledge base and you want it like tailored to your specific case, so model will have that already in its because we are fine tuning it on that particular database. So it will update it in its parameters.
Okay, and for
So
prediction,
Yeah.
yes, I can take that prediction part of it. Yeah. So basically, in terms of predicting, right? What you're predicting is what all things. What would be the course of next actions to be that person, maybe that personality after a few years, right? That is what it is. So that would be, that would probably require, a lot of. Because prediction LLMs are not great at predicting because prediction problems are still something that ML models could do that, and that is also more of like a supervised learning thing where you already have previous data. But here the data, right? Because you're basically talking about human design, like human personality design, right? That is, I don't know if you already have a baseline data that says, okay, these traits would actually make that person get into this, which is, I believe, which is less available. It's not as much available as regular data that we get. Maybe coding problems, you get a lot of code outside. If there's math problems, you have so many math problems in different textbooks. That is easy to get. But to get this data, if you have it access to that data set, yeah, that's fine. We can probably have it predicted, but we can't say how accurate is that prediction because that again has to be compared with the baseline, right? To see, to say, okay, this is this accurate. you again need a denominator saying that, okay, out of these many cases, it was able to predict this. But how do you get that data, right? So that is where the limitation is. And when you're asking this model, this example of Quen, right? This Quen model, what we did here is just we are asking. So these LLMs are more of like next token predictors. They can just predict what is the next token. What we're doing now with this fine-tuning process is we're telling, okay, you're not just predicting what is the next word, but prove your work. You're just asking it proof of your work, how you're trying to get to that conclusion. There is a reason why you see there when you ask it for how many hours in Strawberry, it was just memorizing it, and due to the inherent tokenization problem, it was say, okay, there's only 2. But now it was able to solve it and prove it work and say, okay, it has to be, in order to predict it, it has to think through the problem and then answer it. So you're reducing hallucinations. You're basically building upon this models which are mainly next token predictors to now more of a thinking models where you're build this thinking power where you're thinking and answering the question. Imagine like when imagine just like humans, when we grow up, we memorize a lot of things. We memorize English. First thing is you have to learn English, right? And then what you do is then you build upon that English to do reasoning, to understand math or coding, right? Because then you have to reason through that with the same domain of English. So, and you should also prove your work. But till then, you actually memorize stuff, right? Because in order to learn English, you should memorize what statements are there, how one word has to come later after that. That is how language learning happens, right? So similar way, even this is how they work. Now we are here. Before this, think of this LLMs have just mugged up a
To
lot of
just
things. They
have
can
a
just predict what
minimum
has to be done next.
data
But now
set,
they're actually thinking to the
what's the
problem.
minimum data
That is
set
what
that
RL
will
is
be
actually doing.
required to have the right predictions, have the right denominator? Hello?
Raj, I think if you're speaking, we're not able to hear you. Utkarsh, let me unmute you if you want to hear this. I think
Sorry, my network actually just
I think there was a bad network or something. They also dropped. I think we can take Shubham's question next.
So this is a like fundamental question regarding fine tuning as a concept. So when we define a let's say reward or a penalty, and try it out with every response that LLM generates, right? So what exactly happens under the hood? Like, how does LLM know that if there is a penalty, then probably they need to change their output, or when there is a reward,
Yeah.
they need uh, kind of solidify that concept. So basically, how do
So
how what
yes.
happens at-
Yeah, sure. So I can take your question. I mean, first thing is you probably need to understand basically you need to understand some of the what is RL, right? That is something that you need to understand. So in order to understand what is RL,
Yeah, I think
we are Raj is having a little bit of network issue. One moment, let me I think unmute him.
he got muted, I guess.
Yeah. I'm just unmuting him.
yes, I'm sorry. The today's session actually was supposed to taken by me, but I had to travel somewhere, and that's the reason why Utkarsh is doing this. But yeah, hopefully I'll answer that question. So basically, that's a fundamental question, and it is a good question because I mean you're trying to understand this. So basically, that is how RL works. How is it working? Because in reinforcement learning, what happens is reinforcement learning is more of like learning a game, right? Or like whatever you're playing a game. Like when you play a game, you do a lot of trial and error to learn the game and then play the game and then but imagine that you don't know any rules of the game. You're just going and clicking your buttons and slowly learning the game. So that is what's happening here. These things are just generating random tokens, random for every prompt. It is generating random outputs, and by trial and error, it is able to learn how it can get the inculcate that here. That's happening through something called reinforcement learning. So in reinforcement learning, what happens is for every trial, there is a reward that is given. So if you're doing a positive, if you're doing basically something that is really successful, maybe while playing a game, you were able to win the game, then you get a good reward. If you lost the game, then you basically get penalized for that. So here what's happening is they learn some in reinforcement learning, there's something called policy. So everything happens to this policy. So for every action, what is the for a given state, what is an action that it has to take, and what is the reward? This is how it happens. So given a state of it, what is the next action it took, and what is the reward it got? In the language domain, this state defines the current output of your prompt, and what action is the next prediction of the word, or it could also be the complete output that it generated, and what reward it got. So these are three different things that it will learn together, right? Okay, this is how I generated, this is the reward I got, means I should not generate, I should not generate coding and English together. I should not generate math. I should not generate, math tokens while talking about English, right? Or I should not generate a alphabet when the expected answer is a numeric, right? These are some things which are fundamentally, we are penalizing it and telling it inherently that, hey, this is not the desirable behavior. And in order to get the desirable behavior, how are we enforcing that is through this policy. So the model actually learns that policy to do or to exhibit that behavior. So in our case, in these models, how these LLMs policies are, how these, in our case, the policies are nothing but the model itself. In regular reinforcement learning, because reinforcement learning could be applied for multiple domains. It could also be applied in robotics. But when you're applying that to LLMs, which is a large language models, the policy here happens to be the model itself, the model weights itself. So model weights are nothing but blob of numbers. These are just all matrices and all. So what happens, we need to tweak that parameters of that model. So that is where the LoRA comes into picture. If you saw the diagram where Utkarsh presented, where he was presenting about LoRA, which is low rank adapter, we're just basically changing the numbers. You're back propagating and updating the weights of the model. You can't completely update the weight of the model. You're just updating few parameters of the model and then changing the policies so that it can think through the problem. So now that is what it is able to learn that policy to get the desirable outcome. What is the desirable outcome in our case? In our case, it's a thinking process. We are basically making sure that the model thinks and then gives the answer. And there is and that is how this RL works. So it is fundamentally, you should basically understand how RL works, and then definitely you can correlate all of your understanding here, and it will also make more sense. So whatever notebook that you have, just go through that, and if you have any questions, fundamental questions around RL, like what is this reward, what could be a verifier function, what is a value function. So these are some fundamentals of reinforcement learning that you probably need to understand, then you can probably get more clarity here. But yeah, and that is definitely, even if you are aware of reinforcement learning, sometimes it's difficult to understand because reinforcement learning is really broad area. It could be applied in robotics. It could also be applied in other areas as well. And in this case, it's a large language model domain where where different things mean different things. Like, value function might be something different. Policy might be something different. And in our case, it's a model parameters only, the policy. So that is what's happening. That is what it's updating those numbers to basically a learned thinking process. That is what you can think overall.
Okay. Yeah, makes sense actually. Yeah, would make sense to learn it as a broader concept.
Okay, one more question we had from Adya. She got dropped out in between due to network issues. She wanted to ask a follow-up question. What number of minimum data sets are required to train this model for predictability? All these being confirmed cases making up for a valid denominator. Raj, can you answer that, or Karsh? Raj, I unmuted you. Can you answer it? Karsh, I'll unmute you as well.
Sorry, could you repeat the question? How many number of data sets we require to fine-tune such models?
Yeah, she's asking
Yes. I can
what
answer that
number
question.
of minimum data sets are required to train this model for predictability? All these being
Yeah.
confirmed cases making up for a valid denominator.
Yes, see, the thing is, what happens is this, in this case, number of data set to get the predictability, it all depends on how accurate your prediction has to be. Okay, there are some LLM, some use cases. I don't know. Is Adya not in the call, right? She's not in the call yet.
Adya is
She
in the
dropped.
call. Adya is in the
Oh, she's
call.
in the call. Okay, okay. So Adya,
Yes, yes, I'm here.
research paper.
Raj, your
So
voice is
Adya, there's a
not clear.
research paper which okay. Can not at all clear now? Anything any
Yeah,
better?
it's better. It's better now.
Yeah. So basically, there is a research paper that was published by a finance folks who uploaded all of the financial documents to this LLM, and they asked it to predict the financials for that year,
Hmm.
and it was 70% accurate in doing that prediction. But they were able to get all of the financials for almost last 10 years, and it was 70% accurate. But because financials are something that everyone documents in any firm, right? Because financials are important. They have a lot of financial statements. They just uploaded the statements and just train the model on that financials and then ask, hey, can you predict this? And it was 70% accurate. So in your case, okay, this is basically human behavior, right? How you can engineer someone's human behavior based on what are the series of actions someone has to take to get a specific outcome 3 years from now. Do you have the data? Will anyone document that from the beginning to get that, to be that, right? Maybe there are some YouTube videos, maybe some have some great lessons they might have learned, but even then, there could also be different classes that need to be defined, right? Maybe someone turning out to be something else. I mean, see, I don't know exactly too deep into your human personality or whatever the domain that you were talking about, right? Uh, uh, what was that basically? It was around human
Human
engineering
design.
or human design, right?
Human
So
design.
human design, do you have the data set where you have documented a lot of them? Then you can just try it by not just fine tuning, if that is probably like 100 pages PDF, you can send that 100-page PDF to an LLM and probably ask it. But even if that predicts something, how do you validate it, right? Maybe it will give you a series of actions to be that desirable. Maybe predict it. Okay, if you do this, probably you'll be that, because that is based on the science, right? Okay, in order to be that, this is how you have to change your personality and you will be that destination. But in order to fine tune that or personalize that response, you can still do that because LLMs are really good at it. They can able to combine different facts to come up with a conclusion. So if they might have already learned this human designed domain. All LLMs already have that knowledge. I mean, if you go and ask ChatGPT, it might have already given you answers regarding that human design, right? But only thing is, you will probably need to create more personalized. Maybe it has to personalize for me. It has to know my behavior. Maybe, I have some behaviors which might be conflicting. Then you can apply that to you by adding some more context about you as a person, whether how you need to behave or how you need to change your path to be that end goal of that person. So
You're
that is
very
how,
correct about this. Yes, yes.
yes,
That's
that,
why I have been also considering these differential parameters that would be considered alongside this.
yes. That is a beauty of LLMs. They're hyper personalized. You can make them hyper personalized, and then you can you can apply the knowledge to your own use case, and that is how you can predict it. As I said,
Yeah.
prediction would not be a number here. If you really want a number, that is difficult to get, but at least it can predict what would be a series of actions. At least there's a good chance for you to be that.
Hmm. The thing is that there are a lot of human design experts in the market who work with similar clients over time, over 10, 20 years. So they record the data of their clients' progresses and whatever happens in their life. So those will be the best chance that I can get to have a valid denominator. That's why I asked that what would be a number if I go out and start collecting this. Hello? Hello?
Yeah, Raj, I'm just unmuting him.
Okay.
Yes, there are some problem with this unmuting thing. Okay, but yeah, so basically, I understand. But I don't think everyone would share their data, right? Data is what is important. It's not be in their files, in their laptops. But if they have an open foundation where they want to share the data and create maybe an open data set, then absolutely, there is a very high chance we can do that prediction really accurate as well. Because now it can go more in depth and also have the reference data, isn't it?
Mhm.
Yeah, then it is, but only thing is, who would share the data? It would also have personal information. I mean, PII, you could redact their personal details, probably, and then you can reveal it. I mean, similarly, how medical data set is outside, right? Or maybe a person's, maybe someone has some condition over the years, how that condition has been cured by repeated, maybe, Alzheimer's treatment and everything. It's all over temporal, right? Over time, how it got treated. A series of treatments that come up with some specific result, whether it became worse or it actually helped him. So and everything is personalized as well, because everyone is different. Since you're getting human component here, human itself, every human is different. So everyone would behave in a different way. It is not a financial data which will have a predefined features, because if you take one subject, each human has a spectrum of features. That is the reason why the amount of data that you need will also be immense. Maybe, a lot of data to get it. Maybe internet scale data. That is what's missing out here. Even if you get all of them in the market, all of the data, maybe you could get a pretty good chance of predicting what is it. You can build a model on how you can predict it. But still, it is a hyper personalized response would probably help them out, rather than just giving a number and saying, "Oh, this is how we'll make you this." Because it's also dynamic, right? Anything could change that human behavior later on. Some situation, some environment can change. I would treat that itself to be a RL. There is a reinforcement learning in everyone's mind, because we act in a specific environment and we get a reward. What is a reward? Maybe you're making good money, that might change you, or maybe you got a bad health, that might change your behavior. So based on that reward, your behavior changes. And we don't know what the environment is, because everyone is in different environment. I'm in different environment, you are in different environment, and our reward functions are different. Because some are driven by something and you are driven by something, right? So that makes this subject a bit more complicated and dynamic. But yeah, LLMs already have subject knowledge in it. So you can actually make a human design expert co-pilot. It can help other human designers to get out the best plan for them to be that person.
Probably that's where I can start collecting feedback from the actual experts.
Yes.
How does that start to work?
That will definitely help.
Thank you much, Raj. Thank you. It helps.
How we are able to get to the correct fine-tuning parameters? Is there any shortcuts to that?
There are no shortcuts to get to the actual parameter. It's all about how much compute you're throwing, RL is all about exploration and exploitation. So exploration is about finding all possible solution or all possible ways to explore that huge, vast space of different solutions, and exploiting, which is giving the best reward. So the two things, if you're giving more opportunity for that to explore, then it got different ways of you know or of accruing various rewards, and then exploiting those rewards to maximize that. So that all end of the day, exploitation all depends on how much compute you are throwing at it, how many steps, how much of back propagation that you're trying to do. Because as of now, I think how many steps we did here, 200 steps I guess that we did, or 120 steps to actually convert that model to think. 250 steps. So if you're doing more steps, maybe you're giving it more opportunity to explore and then exploit it, right? Does it make sense? Yeah, that is what RL is all about.
Yeah, and it also depends on how much data you have, because sometimes if you want to update more number of parameters, then you will add more number of layers which you want to fine tune. So it depends upon how much data also you have which you want to fine tune. So if you have less data, so you will not need more number of parameters to fine tune. So you can reduce on the number of layers. Like over here we use 6 layers, and I told you that you can remove query key value and output projection layers. So you can do that as well.
I think next question we have from Rahul. Rahul, you can.
Yeah. Hi, everyone. Thanks for the session. Actually, I hope I'm audible.
Yes, you are audible.
So my question here is, I just started about looking into fine tuning recently. So I see couple of libraries that are there, like Unsloth is there, VLM is there. There is also some packages from Hugging Face as also. So how do you distinguish that which library is used in which use case scenario? Like I understand Unsloth is used to train in a much faster way, where Daniel write kernels in most part, And like, where does VLM fit? Where does this TRL fit? I'm not able to
So,
wrap my head around how this, which library to use, and for which purpose does it, what purpose does it solve?
Yeah. So basically, we should know exactly what module is used for what purpose. VLM is
Yes.
actually for inference only. So it can only infer if the model, because so inference is a process where once the model is trained, you want to get an output from an input,
Yeah. Right.
then that happens. That is what this happens here, right? Based on
Okay.
that is what VLM ensures. It just creation, it loads the model into memory and gives you an output. It is just for inferencing. And
Oh.
coming to Unsloth, Unsloth is a open source project which makes fine tuning with less memory, as much less memory as possible, because they came up with an algorithm, or under the hood they're using algorithm to fine tune any model with very less resources, and they have their own. They came up with their own framework. And TRL is something that Hugging Face came up with, which is only for reinforcement learning. So Unsloth is more of fine tuning. They're not like they're not just specifically for fine tuning, but I'm sorry, specifically for reinforcement learning. But as of now, whatever they develop, the under the hood kernels or anything that they want to fine tune, to exploit the fine tune process with less resources, they're optimizing that for that specific problem. That is what Unsloth is good for. The main purpose of that Unsloth is. Coming to TRL is basically an open foundation model, basically an open source module or library that Hugging Face provided just specifically for reinforcement learning. So they provide a lot of algorithms out of the box that you can use for doing reinforcement learning, like including GPO or GRPO. All of them are actually provided from them as well. But even though if you see the first steps in this collab, if you see the first two steps, they're patching those libraries with their own custom code to make them faster. It's the same library from Hugging Face, but Unsloth is basically patching them by adding their own code base to make sure that it is faster. That is what they're trying to do. So it's more of an optimization problem that they're solving. Hugging Face is already a huge community, open source community, that are providing these packages where we could do this DRPO or any algorithms. Really, anyone can actually do that. That is how it is different. All of these three things are different. So you could probably Google or use any of the AI tools to understand what each and every library is doing. And in this case, we are using VLLM because in GRPO, what are we doing with GRPO? We're asking the model to generate multiple responses given a single prompt, right? So that is what inferencing is, right? Because that is what, when something is giving you an output, it is inference process. That is the reason why we're using VLLM, so that we generate eight responses for one single prompt, right? If you're getting 8 generations for one single prompt, means your VLM or your inferencing process should be very efficient. So that is what they're also enabling. Unsloth is enabling that by having a VLLM that is even more optimized for PRTO to generate much more faster responses than ours.
Yeah. I
Did I
have
make
a
sense?
follow-up as well.
Yes, go ahead. Yeah.
There are, I have come across files which are in a .gguf format and .cpp format. So these are also used at the inference level.
GGUF, right? GG?
gguf and CPP.
Oh,
Llama
CPP.
CPP file. Yeah, the big
Yes.
file. So, so
Yes.
they are utilized at the inference, right? So
Yes, I
what
mean, it
place?
all depends on, how well, where you're inferencing it. And if you're using like any CPUs, so GGUF or even CPP model, so they are basically something that is, let's say that you have, you want to run or have this model inference on basically on small devices, or maybe you want to deploy that on edge devices, then you can, you can basically use these different formats. What they're trying to do is they're basically making the models more efficient. So if it is GGUF, it's basically trying to give you ability to, have these models, optimized for different quantization levels. Like maybe you don't want full scale model, but rather you want like 8-bit or 2-bit quantization of this model. Then what happens is GGF usually have that. It makes that possible by having faster load times or having proper memory mappings and everything. So that is what GGUP is. And whenever you have this LoRA or any of these Q LoRAs which are generated, so usually you probably need to have that, by using GGUP, you can actually, store them in these formats as well. So basically, you can also have like versioning to track different model variations or updates. So all of these are possible because of that. So you're not, every time you don't load full full weight of your model, but you usually have quantized version of your model to save up on the computation. So but you still have to
Yeah, yeah.
balance out accuracy. So GGov actually makes it possible to balance out the computation and also the accuracy of the model. So that is how you see this different formats, which is generated unified format, GPT generated unified format. That is what GGov is.
Yeah, thanks so much. I just have one last question. I'll not take much of your time. So,
Mhm.
see, okay. I was working around with, let's say, DeepSeek R1. So I figured out it doesn't have a function calling as well, and even small models that are used do not have great function calling. So, is there a way where we can, fine tune a model to, let's say I have some custom functions that are there to do a function calling, like fine tuning on
Yes.
for purpose of function calling. Is that possible? If so, how
Yes.
do we do?
Yes, absolutely. I mean, function calling is not it's definitely possible. And you can make even a smaller model excel the bigger model in function calling. And if you're already aware of because all these models that are being developed outside, we say, okay, this model is really good with function calling. Maybe Quen models are really good now with function calling. The reason why is because they have explicitly trained on how to call a function. So they know how to, they inherently possess that behavior to call a specific function. And these are general functions, right? It could either be a simple call. It could either be good with using browsers. There are some models which are only good with using browsers, like Operator from ChatGPT. That is very good with using browser, how to chat, how to enter the details in a browser and get the answer. So that is because that is specifically designed to make that process more efficient. So how they did it? Just by fine tuning. They just have supervised fine tuning, or they could also be RL fine tuning. That is what ChatGPT deep research is doing. They have fine tuned it, or they use reinforcement learning to fine tune that model to do deep research. I mean, they to use browsers to get into links, to click links, and to dig into deeper information. That is what this they have fine tuned for. And yeah, the process also depends on what exactly you want to do. And in your case, if you know there is a specific tool that you want this model to do, then you can actually increase that accuracies to almost 80%, because then you're reducing your domain, right? You're reducing the scope of which tool is it, and you're specifically telling, hey,
Yeah.
this is a tool, this all need to be taught, and then you have thousands of examples on what is the tool, how to call it in different scenarios. And if you're using RL, you probably need lesser computation, because with GRPO you need lesser computation, and there are people already did that, like Search R1. There is a new paper called SCA Search R1. That is basically what they're doing is DeepSeek doesn't have tool calling capabilities, because in the thinking process it can only think but cannot call a tool. But the Search R1, what they did is they taught it on how to even browse. So if you saw this collab, we have given their thinking tags, right, where it is actually thinking to the problem. But now they also introduce a tag called search, where it is actually searching through that problem by using a browser, and then also getting additional context. So they get two different tags. One is to search, the other one is additional context, where they are basically improving on both of them. And they were able to get good accuracy. It's a good paper, I think. Utkarsh can share you the paper for Search R1. I think we also made a video on that, I guess. Maybe a small presentation on that, I believe. I don't know if it's published on YouTube, but yeah, it's a great paper that they just released. And they use the same DeepSeek model to make that, or they use the same process to make it search optimized. So yeah, it is quite possible. By using GRPO itself, it is possible. In that case, if it is RL, then the beauty of RL is you're not asking it to mimic human behavior. Rather, given any use case, it is able to generalize it. And it is inherently possessing those skill set. So imagine someone really good at Googling stuff, right? That is what Search R1 does, because now it can think through the problem just like DeepSeek, but just not think deeper or think through the problem, but also search Google to get the actual response on that problem. So that is what it can do. I'll share the paper shortly.
Okay. Thank you so much, Raj. Really appreciate the insights that you have given. And thanks, Utkarsh, for the demo. And I thank Shivani also, coordinating this thing, these sessions is like, it has a lot of work to do. I appreciate your hard work. Thank you so much, guys.
Yeah, thank
Yeah,
you for
thank
being
you,
part of
Rahul.
this. Thank you.
Yeah, next question we have from Nivedita.
Yeah, Nivedita.
Yes, Nivedita, go ahead. Sorry, Nivedit. Okay, go ahead, please. Sorry.
Oh, sorry, Nivedita. I'm sorry.
May I know, so after fine-tuning the model, so if I want to run that in a local machine without a GPU, is that possible? So I will not take a very big model, so I will take 2.5, upward of 0.5 billion parameters. Is that able to run in a non-GPU machine or non-GPU instance?
Yes, you can run it on a small GPU machine, but it all depends on how fast, how many tokens per second you need and all. But you can also use Olama, right? Because Olama already provides way to run them in on your machine, but also you need to choose which quantization that you're looking for. Are you looking for 4-bit quantization or 8-bit quantization? Because the quantization does make difference. Because then if it's 4-bit, then it can really run faster. 8-bit will also run in your machine, but it might take maybe a few seconds to generate one token. Maybe it can generate like 10 tokens per minute. So it all depends on your performance that you need, and also depends on the machine that you have. If you're using Mac with M4 and with 32 GB RAM, then they're quite a big model, quite a lot of models with this. Like Quen 2. This a smaller model can definitely fit in that. It hardly requires 8 GB memory. That can definitely fit that and probably run it on your laptop as well with 32 GB RAM.
Any question?
Yes, I'm quite new to these LLMs and all. All I could do was connect with Olama and do DeepSeek with some tutorial. All I could do is that. I'm running a small training institute, and I would like to create some AI-based LLM that could automatically teach students. So, can you give me some recommendations where I could start with this LLM? Because LLMs can be fine-tuned as a teacher as well, right?
Yeah.
If I'm not
See,
wrong.
okay. Yeah, yeah. So if you want to fine tune any LLM model and you want to customize it, so there are these options like either you should have a data set on which you want to fine tune it. But if you want to specifically fine tune it such that it is responding as per your specific requirements, like if you want to teach in a way, a particular subject needs to be taught, how it should be taught, what things need to be covered, and all of those things. So there are many frameworks and many frameworks which have come. There's something called Crew AI. So these LLMs can be integrated using Crew AI, and in Crew AI you can give a detailed prompt for like which details your requirements, and the LLM will then give a response according to that particular requirement. Even you can use LangGraph and LangChain methods as well for them. Through AI is something very seamless to facilitate this.
Can you spell that, please? Through?
Yeah, sure. I can write it over here in the chat so that you can now. Yeah.
Okay, through AI. There are a lot of language models like GPTs
Yeah.
and DeepSeek, which is open source. I could run that in my system itself. Which should I choose? Because I can't invest more on GPUs, CPUs, and more. I have financial constraint also. Which model should I use? How to choose the model actually?
You can actually choose the model like, for example, if you want to choose a model which has capabilities at par with DeepSeek, so there's something called distilled models as well. So if you don't want to invest so much money into larger models, so you have Quen 32 billion parameter model, which is a distilled model. It takes the parameters from the larger model, which is like the DeepSeek model, which has 671 billion parameters. You take some parameters from that model, and on top of that, you can retune it. So there's something called as open router, and on open router, you can use these models for free using the open router API. So they list a lot of these models, Like you can use the Quen 32 billion parameter distilled model, which takes these parameters from the DeepSeek model. So you are like using a model which is at par with the larger models.
Can you spell that opener router? Is it?
It's open router. I'll just
Okay. Thank you. Thank you so much.
Thank you, Ramya. Any other questions anyone has? Okay, then I think we can call this at the end of the session. Thank you everyone for joining. It was a really great session. Have a good weekend. Thank you, everyone.
Thank you everyone for joining.